Hello and good day to everyone. Welcome to our second part of our video on lecture 2, which is all about fluid mechanics concepts. So we could see from our outline that we are already done with the basic flow relationships, also the different types of pressure, and the Bernoulli's equation. This time around, we will be going to discuss the friction factor and frictional head losses. Okay. So what are the equations involved and how is it important to consider friction in terms of our calculations? Specifically, this section deals with the calculation of airway resistance and frictional losses based on different parameters: the shape and length of the airway or duct, the roughness of the surface, the flow regime that is applicable, either turbulent or laminar, and the quantity of air, gas, or fluid in the airway or the duct. Let's go through this one by one. Okay, so we're going to talk about frictional loss, and in order to understand this better, we need to introduce Reynolds number and its relationship with turbulence. Okay, so we could see here that the degree of turbulence in a moving fluid depends on two parameters: the viscosity and velocity. The figure on the left shows us a low velocity laminar flow, and the figure on the right shows a high velocity turbulent flow. So when a fluid begins to move, individual molecules or the layers start to move over each other in an approximately linear fashion. We know that in fluids, the distance between the molecules of the material are in such a way that they can move past each other, as compared to a solid wherein the molecules cannot move, no? Okay. So as the individual molecules or layers start to move over each other in an approximately linear fashion with retardation dependent on the internal cohesion between the molecules, this is termed as the viscosity of the fluid. So viscosity as a term refers to the cohesion between the individual molecules, okay, in the material. So it starts out as movement in a linear fashion. This is true with low velocity laminar flow. But as the velocity of the fluid increases, the molecules or layers move in an increasingly random fashion. Okay, so it becomes more random when there is an increase in velocity, because as the velocity of the fluid increases, there is also an increase in the inertial forces between the molecules, and the flow becomes a turbulent type of flow. So less viscous fluids moving faster are more turbulent than more viscous fluids moving slower. So the viscosity talks about the cohesion between individual molecules. So the more viscous it is, then the higher the cohesion. Ibig sabihin, the cohesion between the molecules prevents it from moving more freely. But when you have less viscous fluid, then they could move past each other because the cohesion is lower. Also, the randomness in terms of the movement in a turbulent flow increases, because when you have a higher velocity, then the inertial forces between the molecules also increase. The inertial forces causes more randomness in terms of where the molecules will be situated. Okay? So we could see that turbulence is associated with energy or pressure losses. And a number that defines the ratio of inertial to viscous forces is termed as the Reynolds number. In equation form, it is expressed as the Reynolds number is equal to rho times L times V over mu, where the rho is the fluid density expressed in kilograms per cubic meter. L is a characteristic dimension, okay, expressed in meters in terms of SI. For example, diameter. V is the velocity of the fluid, okay, and mu is the viscosity in terms of kilogram per meter second, or this is 1.8 times 10 to the negative 5 for air. Okay, so it depends on what type of fluid is considered. Different types of fluids have varying viscosities. Okay, so this is the inertial forces, and of course this would be the viscous forces or the viscosity of the fluid itself. Okay, let's proceed. In laminar conditions, the pressure loss is proportional to the velocity. In turbulent conditions, the pressure loss is proportional to the velocity squared. And turbulent flow starts between Reynolds number 2000 to 3000. So we could see from the graph a plot of pressure loss versus fluid velocity. The relationship between pressure loss and fluid velocity is linear if the flow is laminar, or there is laminar flow in this part. Okay, between these values 2000 to 3000, then it becomes turbulent flow, and the relationship becomes the pressure loss is directly proportional to the velocity squared. Okay, laminar flow, the relationship between pressure loss and velocity is linear, while in turbulent flow, the relationship between the pressure loss and velocity is the square of the velocity. Okay, so it is this would be parabolic in a graph. Okay, so we proceed talking about frictional loss and hydraulic diameter. In circular ducts or airways, diameter is the characteristic dimension L. Okay? In non-circular ducts or airways, an equivalent or hydraulic diameter is used. Of course, when you have a circle, okay, then its characteristic dimension would be its diameter. Okay, this one. But for an irregular, for example, no, na tunnel or duct, then we need to express it in terms of an equivalent or a hydraulic diameter. Okay, how do we do that? This is expressed in terms of 4 times the area over the circumference, and this is expressed in meters. How did we come up with this particular relationship? We'll try to derive this one. The equivalent hydraulic diameter is the diameter of a circle having the same ratio of area to circumference as the shape being considered. Okay, so we could just see that the hydraulic diameter has the same ratio of area to circumference as the shape being considered. For example, rectangular tunnel or semi-rectangular, okay, tunnel in terms of metallic mines, no? Metalliferous mines. This one, since this is a softer deposit, like for example coal, then we could have a more uniform shape for our tunnels. Okay. So based on a circular cross section, that is a cylindrical duct, for example, or raised boreholes, okay, then we could determine the parameters that has the same ratio of area to circumference as that of a duct or airway with a circular cross section. So we know that the area of a circle is pi r squared, right? Okay. But this is also equal to pi times the diameter over 2 squared. This gives us pi d squared over 4. How about for circumference? The circumference of a circle is just pi d or 2 pi r. Okay, so since we are considering the same ratio of area to circumference, then for a non-circular profile, then we could compute the hydraulic diameter. So this is for a circle. For our non-circular body or opening, then we could have A prime, which refers to the area of this non-circular opening or duct or airway, and we could also express the circumference, or let's say the perimeter of this non-circular duct or airway as P prime. So we could have the ratio of the area to the diameter, in this case termed as a perimeter since it is not circular, would be or should be equal to that of a circle, okay, which is this one, the area and the circumference. And since we know that the area is equal to pi d squared over 4 all over the circumference, which is pi d, then this becomes pi cancels out, square cancels out, then what is left is d over 4. And we could rearrange this for d. So if we arrange this, this becomes 4 times A over C is equal to D. And this gives us the hydraulic diameter for a non-circular opening or airway. Okay? So you could see that it would be the same as this one. 4 times the area over the circumference. Proceed. Okay, so we have an example that requires for us to calculate the velocity and the quantity of air required to create turbulent flow. Reynolds number equals 2,500 in a 3 meter high by 5 meter wide development profile. Assume the density of air equals 1.16 kilograms per cubic meter and the viscosity of the air equals 18 times 10 to the negative 6 kilogram per meter second. So we could use our equation RE, or the Reynolds number, is equal to, of course, the inertial over the viscous forces. So inertial refers to rho LV over mu. And this could be expressed in terms of viscosity. This would be the density times the characteristic dimension or length times the velocity. So we want to find for the velocity and the quantity later on. Okay, so we know that in this case, to rearrange, we could compute for velocity by multiplying the Reynolds number equal to 2,500 times the viscosity over the density times the characteristic length. We have discussed a while ago that the characteristic length can be expressed in terms of the hydraulic diameter for non-circular cross sections of ducts or airways. However, the characteristic dimension L for circular cross section would just be its diameter. Okay, so since we have a non-circular airway having the following dimension, so it's a rectangular development profile, then we could compute for the hydraulic diameter to solve for the velocity. Okay, so we know that in calculating for the hydraulic diameter for non-circular airways, we just use the equation 4a over c, or the perimeter. Okay, so for a 3 by 5, okay, so this is 5 meters, and in height it is 3 meters. So area is equal to, of course, just multiply the length times width, 15 square meters, while for the perimeter, or for this C, we have 2 times 5 plus 3, which is 8 times 2 is 16 meters. Okay, so we could now compute for the hydraulic diameter to be 4 times 15 over 16, which gives us 3.75 meters. So this would be substituted to our L over here. Knowing that our equation to use is this one, okay, our viscosity is 18 times 10 to the negative 6 over the density, which is 1.16, and we know that the hydraulic diameter is 3.75. The velocity is given to be 0.01034 meters per second. Okay, so we have already computed for velocity. How about for quantity? How do you compute for quantity again? Quantity is just the velocity times the area. Okay, so Q is equal to VA, and the velocity is 0.01034 meters per second, and the area is, of course, 15 square meters, and could compute for the quantity to be 0.155 cubic meters per second. Okay. So as easy as that, we could see that indeed this is a turbulent type, okay, of flow, because it is between 2000 to 3000 in terms of Reynolds number. This is for turbulent flow. Below this one, of course, we have the other type of flow, which is the laminar flow. Okay, so let's proceed. Surface friction. Frictional pressure loss represents a loss of energy to the system. Okay, so this results in a loss of static pressure, which is not reversible. And in turbulent regimes, the loss is proportional to the square of the velocity. And since nearly all mining applications are in this regime, turbulent flow can be assumed and the square law applies. Okay. So normally, the equation is written in terms of quantity, although the effect is due to the velocity. Okay. So just to reiterate that in nearly all mining applications, the type of flow that is governing the mechanics or the movement of the fluid is turbulent flow. And we assume that the square law, or that the pressure loss, is directly proportional to the square of the velocity in the ducts or in the airway, okay, or in mining applications. So since we know that the relationship is the square of the velocity to the static pressure loss, and we also know that in the equation for quantity is the velocity times the cross-sectional area, then in terms of quantity, the relationship between static pressure loss is equal to the resistance times the square of the quantity. And the resistance is expressed in Newton second square per meter to the 8th power, and expressed in terms of a unit termed as joules. The resistance of an airway, pipe, or conduit depends primarily on the following parameters. First is the cross-sectional area. Second would be the shape, or the ratio of area to perimeter. Okay. We term this as our hydraulic diameter. The length, of course, of the airway, and also the roughness of the surfaces. We already have an idea of this. The more rough a surface is, the higher the friction. And also it is dependent, or the resistance is also dependent on the density of the fluid or the gas. Okay, so try to remember these things. The Atkinson's equation by Atkinson in 1854 is the mathematical representation of the relationship between frictional pressure loss occurring on rough surfaces and that of velocity. The equation R is equal to K times C times L over A cubed times rho over 1.2. And this is expressed in terms of joules. R is the resistance, again expressed in Newton second square per meter to the 8th. K is the roughness factor. Its range is from 0.003 for smooth ducts to 0.015 for rough walls. And this can be obtained from reference books, but site direct measurement is preferred. So there are methodologies in order to obtain the roughness factor. The C, right here, is the cross-section circumference, and L is the airway length in meters. Also, the A is the cross-sectional area in square meters. We could also express it in terms of pressure loss. P is equal to KCL over A cubed times rho over 1.2 times Q squared in terms of pascals, or P is equal to KCL over A times rho over 1.2 V squared, also expressed in terms of pascals. What is the importance of this Atkinson's equation? Okay, so for example, we have a duct, a rectangular duct. Then we could characterize the parameter C times L as the area of the rubbing surface. So this would be the circumference times the length of the duct, no? So ano yung mga surface that would be exposed to the moving fluid, for example air, in our ventilation ducts? So the circumference or the perimeter in this case, since it is rectangular, multiplied to the length. Okay, so in essence, this would be all the surfaces that are rubbing with the fluid. Okay, so that would be the area of the what we call the rubbing surface. The K is a factor depending on surface roughness, and it is also convenient to characterize airways with resistance per 100 meters or R100. Okay, so if you see R100, then it is just a representation of the resistance for a 100-meter length. Okay, so this would be 100 meters. If it's R100, then it is for a 100-meter length airway. Okay, so what is the resistance per 100-meter length? That is R100. And next is K factors can be obtained from textbooks but should be checked by surveys. So let's proceed. Another example. The friction factor K for a 3 by 5 meter airway profile is 0.012 newtons second squared per meter to the fourth. If the air density is 1.17 kilogram per cubic meter, what is the resistance R in newton second square per meter to the 8th of a 100-meter length of the airway? Okay, so how do we go about computing this one? Okay, so we know that our formula, Atkinson's equation, is R. Okay, so for 100-meter length, so this is R100, is equal to KCL over A cube times rho over 1.2. Okay, so we need first to compute for A as well as the C, or the area in the perimeter. Okay, so the area is equal to 3 times 5, which gives us 15, and C is equal to 2 times 3 plus 5, which is equal to 16 meters. Area is square meters. Okay, so now we could compute for, I think everything is already given. K is equal to 0.012 right here, or the friction factor. C is equal to 16 times the length, which is 100, over the area, which is 15 cube, times rho density 1.17 over 1.2, which is a constant. So this gives us 0.005547, and our unit is joules. Okay, so that would be our final answer. Okay, next. What is the frictional pressure loss when a ventilation rate of 45 cubic meters per second flows through 450 meters of the airway? Okay, so since what we obtained is R100, so this is in terms of 100-meter length, we could make use of the proportion, okay, for a 450-meter length. Okay, so R450 is therefore equal to R100 times 450 over 100. As simple as that. So R450 meters is equal to R100 times 450 meters, since that is the length that we want to examine, over 100. So we know that R100 is equal to 0.005547 times 450 over 100. This is equal to 0.025 Newton second square per meter to the 8 or joules. Okay, so since we know the resistance already, okay, it asks us to compute the frictional pressure loss. And we know that the frictional pressure loss as related to resistance is equal to RQ squared. But the Q is given 45 cubic meters per second, so we could compute for the pressure loss, frictional pressure loss. And this would be equal to 0.025 times Q squared, which is 45 squared, and this gives us 51 pascals. Okay. Right, so that is how we could make use of our two equations, no, in terms of the Atkinson's equation and this relationship P is equal to RQ squared. Next, so we proceed to surface roughness and K factors. So K is a factor depending on surface roughness height and airway dimensions. Okay, and this has or this can be expressed in terms of the following equation. K is equal to this is a relatively long equation, 1.74 minus 2 log base 10 2e over 1000 hydraulic diameter quantity squared all over 6.67, and it's expressed in terms of Newton second square per meter to the 4. Okay. K is the friction factor. In Newton's second square per meter to 4. E is the surface roughness. In meters. And D sub H is the hydraulic diameter. Also expressed in meters. Okay, so just take note of this equation for the K factor, the friction factor. The calculations allow K factors to be estimated if unknown or results of direct measurements reconciled with observation. The concept is that in turbulent flow regimes, the K factor can be calculated from surface roughness height and airway or duct size. For non-circular shapes, the hydraulic diameter is used, and it is equal to 4A over C, and E is the surface roughness. Okay, so this just relates the importance of K factors. For most mining applications, the friction factor K is essentially constant for a given ratio of roughness height to a diameter, and the square law applies. Some approximate roughness heights in millimeters are as follows. We have the types of airways or ducts on the first column, and its approximate roughness height in the second column. Just take note of this range of values for each type of airway or duct. Okay, So the K factor is constant with E over D for mining applications. Again, E is the surface roughness and D is the hydraulic diameter. So this ratio of surface roughness to hydraulic diameter is quite important. Okay, so let's have an example. So in this figure, determine the K factor for a 610 millimeter diameter fiberglass duct with E or roughness equal to 0.3 millimeters from the figure below. Okay, so since we have a 610 millimeter diameter na fiberglass duct, so its surface roughness E is therefore equal to 0.003 and its hydraulic diameter, since it is circular, then we make use of that diameter given, which is 610 millimeters or 0.610 meters. Okay, so these are all expressed in meters. Therefore, we could compute for E over D equal to 4.918 times 10 to the negative 4, and given from the figure. Okay, so where do we look at? So since it is mentioned here that we are looking at a turbulent flow, and in terms of mining applications, then we will be looking at, where's this one, times 10 to the negative 4. So this gives us 4918 0.0004 in between this one, right? 0.001 and 0.001, somewhere in between, right here. It's E over D, and we want to determine its friction factor, and this would be approximately equal to, okay, so if we look at this level, approximately equal to this part in terms of our friction factor, 0.0025, okay, approximately equal to 0.0025 Newton second square per meter to the 4. So what is important is that in order to use this diagram or graph, we compute first for E over D, okay, and this is a graph that relates the E over D with that of the Reynolds number and the friction factor. Okay, so friction factor is approximately at this level right here. Next. Okay, so we're asked to calculate the K factor for a 3x5 meter development profile with surface roughness E equal to 125 millimeters. So for the development opening, the cross-sectional area is equal to 15 square meters since it is 3x5. Okay, and its perimeter is again equal to 8 times 2, 16. Okay, given this, hydraulic diameter is given to be 3.75 meters, and this is what we need in terms of determining the ratio of roughness to hydraulic diameter. which is 0.125, or this one, over 3.75, and this gives us 0.0333. Okay. Plugging in to the equation to determine k, so we write it as 1 over square root of lambda is equal to 1.74 minus 2 log base 10 to e is equal to 1.74 minus 2 log base 10 2 times 0.0333 is equal to 1.74 minus negative 2.361, which is equal to 4.1. Therefore, lambda is equal to 1 over 4.1 squared, which is equal to 0.0595, but k is equal to lambda over 6.67. Therefore, k is equal to 0.0595 over 6.67, which is equal to 0.00892 Newton second squared per meter to the 4. Okay. So this gives us the value for k for a 3x5 development profile with surface roughness of 125 millimeters. Okay, we have another example right here, another type of diagram. Okay, so given a 15-meter section of pipe with an airflow of 200 cubic meters per hour, and suppose that the air duct diameter is 200 millimeters and airspeed is 1.95 meters per second, we are to determine the pressure loss for the 15-meter section of pipe. So we could see from the diagram that it is quite a different type of values that are presented in the different axes. Okay, so we could see here that this is in terms of pressure drop, delta P in pascals. Okay, just disregard this temperature right here, and also in terms of the x-axis is the air capacity in cubic meter per hour, or also referred to as the quantity. These lines, okay, represents diameter. Okay, so lines aligned this way represents the different sizes for the diameter of the pipe. Okay, so if we're looking for an air duct with a diameter of 200 millimeters, then we're looking at this particular line here. Okay, since this is representative of the 200 millimeter diameter air duct. The other lines, okay, right here would represent different speed or velocity of the air inside the duct. Okay, so if we are to look at 1.95 meters per second given airspeed, then we're going to look at which line? Okay, 1.95. So it would be, this is 3 meters per second, this is 4 meters per second, 5 meters per second, so on. So around this area is 2.5 meters per second. Okay, so since we are looking at a 200 millimeter duct at 2.5 meters per second, so they would intersect here. Okay, so we could now determine the pressure drop, okay, by looking at the y-axis, and we could see that the pressure drop is approximately equal to 0.21. Okay, so it's approximately equal to 0.21 pascals per meter. Okay, so this is for 1 meter long pipe, no? So all these graphs are for a 1 meter long pipe. So this is expressed in terms of per meter. So for the 15 meter section, then you just multiply 0.21 pascals per meter times 15 meter long section, then the pressure drop is equal to 3 pascals. Okay, let's have another example. 20 meter section, airflow is 570 cubic meters per hour, and the duct diameter is 250 millimeters. The airspeed is 3.23 meters per second. Okay, airflow is 570. Okay, around this value. We're looking at 250 millimeter diameter, which is this line, and airspeed is 3.23 meters per second. This is 3, this is 4, around this value. Okay, so that's 3.5 around this value. Draw a parallel line, it would intersect on that part. Okay, and now we could get it on the y-axis, which is approximately equal to 0.9 pascals per meter. So for the 20 meter section, just multiply 0.9 pascals per meter times 20 meters, cancel meters, this gives us 18 pascals. Okay. So if we're given this type of diagram, we could now determine the total pressure loss for a given length of a pipe. Okay, we now proceed to shock losses. Shock losses occur due to the flow separation and impact due to changes in direction of an airflow. So the equation for shock loss is equal to x times 1/2 times rho v squared. And x is the shock loss factor. This is obtained from charts corresponding to the geometry of the component in question. Rho is the fluid density in kilograms per cubic meter, and v is the fluid velocity in meters per second. The shock loss, it's important to note this one, is that it is in addition to surface frictional losses. So we've discussed surface frictional losses a while ago, and its corresponding details. The shock loss is another type of loss that is added to the surface frictional losses. So since x is the shock loss factor, it is different for each object having different geometries. Okay, So, for example, in the pipe, okay, if you have an inlet, then different types of inlet shapes or cross sections will have different X or shock loss factor values. Okay, for a circular cross section, we have and a sharp edge with this particular orientation, then X or shock loss factor for this diagram is 0.9. If the cross section is square, it is larger, 1.25. For a flange, okay, na pipe, shock loss factor is 0.5 if the cross section is circular, 0.7 if it's a square. For a bell mouth, okay, then the shock loss factor becomes minimal, no? 0.05 to 0.1. For conical, it's 0.3 to 0.5. So this explains that for inlet, in order to minimize shock losses, it must have as much as possible gradually decreasing diameter, okay, for the inlet. Okay, so this helps in reducing, no, the shock losses in our ventilation pipes or our ventilation airways. For an abrupt expansion or contraction, okay, we look at the area of the cross sections. A1 refers to the cross section for the left part, while A2 refers to the cross section of the right part. For an expansion wherein there is an increase in cross-sectional area from A1 to A2, then we use the ratio A2 over A1 and use this graph to determine the shock loss. Okay, so the larger the ratio for an expansion, the larger also the shock factor. Same goes with for contraction. Okay, so we just need to look at the ratio and look at this corresponding graph to determine the shock factor X. For a bend of uniform cross-sectional area, depending on if it is a circular pipe or a square or rectangular pipe, the sharper the bend, okay, then the greater the shock factor X. Okay, so if the angle alpha here becomes increasingly larger, okay, so if we compare this bend to a bend that is 90 degrees, then we will have a greater shock factor X for a 90 degree around this part, okay, for taking consideration, for example, than that with a more smoother bend, no? Or less alpha, less angle in the bend, like for example 20 degree bend. So a 90 degree bend will have a higher shock factor X as compared, for example, for that of a 20 degree bend right here. So refer to the graph to determine the shock factor X. Also for junction and intersections, okay, and outlet loss with diffusers. Different angle for the diffusers will have uh, differing values for shock loss factors also. Okay. Okay, so we have an example. We are to determine the shock loss factor for a 90-degree bend in a rectangular duct. Okay. So the shock factor for this one. So the rectangular duct would have a graph here on the green part, since this is for the rectangular cross section, and 90 degrees. Plot that with the green graph, green line, and the corresponding shock loss factor is approximately equal to 1.6. Okay, so as simple as that. Pressure losses due to obstructions. So in intake shafts with cages or those with mine conveyor belts, a significant pressure loss can be associated with the degree and type of fill in place or obstructions that are present in the tunnel. Air velocity determines velocity pressure, and an obstruction will result in a pressure loss due to separation and skin friction. Okay. So we could see from the diagram the effect of any obstructions in the airway for an airflow that would hit the obstructions. Right. Pressure losses are determined by the shape of the obstruction, the amount of obstacles that fill the airway, and also the velocity pressure impacting on the obstruction. Pressure loss due to a transverse obstruction is a function of its frontal area, shape, and velocity impacting on the facing edge. Okay, like this for example. Pressure loss due to longitudinal objects result from the reduction in cross-sectional area and increase rubbing surface. So for longitudinal objects that have an orientation in line with the flowing fluid or the velocity of the fluid, then it would be due to the increased rubbing surface. Method used to calculate frictional loss due to conveyor structure or shaft furnishings. Okay, so if you have pipes that you are going to install in your shaft, or for example the cage, what would be its effect in terms of pressure losses by installing these structures or furnishings inside the shaft? Then this is the method on how to determine that particular parameter. The calculation method is based on the standard shape drag coefficients. Okay, so the drag coefficient C sub D is given for different shapes like I-beam, square shape, rectangular shape, circular shape, a plate, a streamline shape, and flanges. Okay, so just take note of the drag coefficient for these different types of shape. The pressure loss for transverse members is again related to the velocity pressure. The velocity is calculated in the free airway area or the net of longitudinal members. And so the pressure loss is given to be C sub D times rho V squared over 2 times A naught over A, where P is the drag coefficient times the velocity pressure times the fraction of the area filled. Okay. The coefficient of fill is the amount of cross-sectional area occupied by the members. And this can be written for pressure loss in terms of quantity. Okay, so we have that expression which relates it to the quantity of the fluid. Okay, so we have the following. C sub D is the drag coefficient, C sub F is the coefficient of fill, and C sub F is the ratio between the frontal area and the cross-sectional area of the airway. The frontal area is, of course, the area that is blocking the moving air. Rho is the air density, A is the airway cross-sectional area, and Q is the airflow quantity. The base case drag coefficients must be corrected for aspect ratio C sub D. Okay? So the drag coefficient needs to be corrected to account for the effect of geometry. The corrected C sub D is equal to C sub D times C sub HW times C sub SW. C sub HW refers to the correction for height to width ratio, and the C sub SW is the correction for spacing to width ratio. This is due to the effect of the height to width ratio and the spacing to width ratio. So we could see from the diagram here on the right that C sub D increases with length for a given width. So C sub D reduces with increased height to width ratio until surface friction becomes significant. For spacing, C sub D reduces with closer spacing due to mutual interference. Okay? So the higher the spacing, the higher the correction for spacing to width ratio. Pagka masyado silang magkalapit, parang pareho lang sila na you take them or you consider them as only one obstruction kasi masyadong maliit na yung S, like this for example. Alright. So we have an example. A 2.5 kilometer long coal mine gate road is to be supported with concrete filled pipes during longwall retreat. The pipes are 800 millimeter diameter and are located at 4 meter spacing for 500 meters out by the phase line. The airway is 2.5 meters high and 5.4 meters wide. The airflow rate is 45 cubic meters per second and the air density is 1.2 kilogram per cubic meter. We are to calculate the total pressure loss along the 500 meter supported gate road. We could see that in the cross section right here that the airway is 2.5 meters high and 5.4 meters wide. Okay, and so the post or the supports will be installed relatively offset to the right. Okay, and 0.8 meters in diameter. What would be the effect of these obstructions in when we have this type of okay, so it's like we have posts that would be installed, okay, at 4 meter intervals, okay, and the velocity of the air goes towards the phase line, okay, and this would of course create an obstruction to the airway. So we are going to determine the pressure loss due to the obstructions as well as the pressure loss due to the friction of the rubbing surfaces, this one, and as well as the floor. Okay, so total pressure loss is what we want to calculate for. Alright, so we start by determining the total pressure loss is equal to the pressure loss due to the obstructions plus the pressure loss due to friction. And the pressure loss due to the obstruction P ob is equal to CD corrected times CF times 1/2 times rho A squared times Q squared. Okay, and we know that the corrected C sub D is equal to C sub D times C HW, or the height to width ratio, times C sub SW, or the spacing to width ratio. C sub D is equal to 1.2 And if we are going to look at the height over the width, the ratio of the height to width is equal to, so this would be equal to 0.8 over 0.8, which is equal to 1. And if we refer to the figure, C sub HW is equal to 1. Okay, the spacing over the width is equal to 4 meters over 0.8, which is equal to 5.0. And if we look at the diagram before, then C sub SW is equal to 0.2. Therefore, the corrected C sub D is equal to 1.2 times 1 times 0.2, which is equal to 0.24. Okay. We could also compute for the frontal area, A, which is equal to 2.5 times 5.4, which is equal to 13.5 square meters. And we know that C sub F is equal to A naught over A, which is equal to 2.0 over 13.5, which is equal to 0.148. So we could now compute for the pressure loss due to one pipe support, and the pressure loss from our equation before is equal to C sub D corrected times C sub F times 1/2 times rho over A squared times Q squared, and this gives us 0.24 times C sub F, which is 0.148 times 1/2 times rho 1.2 over A squared 13.5 squared, and this gives us 0.234 pascals. Remember that this is for only one pipe support. So for a 500 meter length tunnel, we could see that there are how many posts? Number of pipes required, that would be 500 meters length, and the spacing is 4 meters, so that gives us 125 na pipes, no? So the pressure loss due to 125 pipe supports would be equal to 125 times 0.234, and that would be equal to 30 pascals. So that would be R for the obstruction. Next one, we're going to calculate for P sub F. Okay. P sub F is due to the friction, and make use of Atkinson's equation, which is KCl over A cube times rho over 1.2 Q squared. The perimeter is of course 2 times 2.5 plus 5.4, which is equal to 15.8. And so we could now express it in terms of P sub F equal to K is 0.009, C is 15.8, L is 500 over 13.5 cube times 1.2 over 1.2 times 45 squared. Okay, so this gives us 59 pascals. Therefore, the total pressure loss is equal to 30 plus 59, equivalent to 89 pascals. Okay. So that is how to compute for this particular example. I think that would be all for topic number 2 for our lecture 2, which is on fluid mechanics concepts. Prepare for a quiz for lectures 1 and 2 in the coming days. I'll just post further instructions in our LMS. Okay. And see you on the next one.